Hello. So we want to continue with our lecture on the hyperbolic equations. We'll look at a model problem and how to tackle that with the method of characteristics. Okay, and then perhaps we may move on to the finite difference approach to dealing with it. Okay. So our model problem is given by this advection equation: du dt plus c du dx is equal to 0. This is the initial condition. Ux at t is equal to 0 is u naught at x. Okay. Now it's easy to check by direct substitution that if you sub in u naught at x minus ct into this equation, it satisfies it, and of course it satisfies the initial condition to show that this is a solution. Okay, so that is what we've done here. It's easy to check it. So you can basically let xi be equal to x minus ct. So you have u naught at xi. So you can find du dt and find du dx and see whether when you sum these terms it goes to 0. So du dt, of course, would just be du naught dt, okay, from there, which is du naught xi, dxi dt, but the xi dt is negative c, so that gives you this minus c du naught dxi. Then you can find du dx as well. Du dx would be du naught dx, which is equal to du naught dxi, dxi dt, dxi dx. Dxi dx is just 1, and so you are left with this. So if you multiply this by c and add it to this, that gives you du dt plus c du dx, and that is this term plus that, which is equal to 0. Which means that this equation basically satisfies that and satisfies the initial condition. So by direct substitution, we can easily check that the solution to this advection equation is basically given by this function, the initial condition with an argument x minus ct. Okay. Now, we want to actually show this, prove this, or derive this, and show that the solution using the method of characteristics is this. That is what we do next. Okay. Now, if u here, which is a function of x and t, okay, is a function of two variables, of course, and if x is equal to x as a function of t defines a smooth curve c in the xt plane. Remember, we said that the solution to the PDEs is a surface, and on the surface you have characteristics curves. All right, so this is a surface, u here is a surface. Let x is equal to x of t be a curve on that surface. Okay, a smooth curve. Then the total derivative of u, right, the function u, or if you like the solution u along the curve c, is given by this, right? The total derivative du dt will be the partial derivative du dt, and then dt, which is 1, so it doesn't appear here, plus you have du dx and multiply by the x dt. Okay, so this is the total derivative of u. So we see that equation 5 actually defines how this u changes as you move along c, as you move along that curve. Curve. Now, by comparing equation 3 and equation 5, you can see that 3 is basically a total derivative if the u dt is 0, and also if the x dt is equal to c, because basically you have the u dt, which is this, you have the u dx, which is also here, so basically c here is the x dt. So this can be interpreted as the total derivative of u, where the u dt is 0 and the x dt is equal to that constant c here. Okay, so another way to interpret this is written down here. So it's basically the u dt is 0 along the curve, the x dt is equal to c. All right, so take time to understand this. This is very important. What it means is that the solution, as you move along the characteristics curve, which is given by this, or if you like this, as you move along it, the solution is constant. U there is constant. It doesn't change with time. All right. along this curve. If you solve this, you get the x minus ct is equal to xi. Xi, of course, is when t is 0, x is xi. Okay, so xi here is constant. So this equation here, or if you like here, is a characteristic equation with a speed of c and a slope of 1 over c. All right, the slope is 1 over c because we are looking at the xt plane. All right, so if you like t as a y, x is on x. So this is a characteristic curve or equation or the line. All right, so any point along this line here, u is fixed, is constant, the solution does not change. That is important. Okay, so it's constant along the line. So how do we get a solution from it? Now we know that when t is 0, u is given by u naught as a function of x. Okay, which means that u xt, because u is not changing, it can take the value at the initial point, right? But at the initial point, x is xi. So at t is 0, you can plug in xi, and that is given by this. Now u is equal to u naught, right, initially. So we can basically say this is equal to u naught. Instead of x, we have xi, because that is the value at t equals 0. And then just replace xi by its value, which is x minus t, and you have u naught at x minus ct. So u is equal to u naught at x minus ct is the solution of the equation. And this is, remember, this is the same solution we got when we just did the direct substitution. So by the method of characteristics, you can actually show that u naught x minus ct is a solution to the simple advection equation. Okay, good. Now, what does it mean? What it means is that, note that we just said du dt is 0, the total derivative is 0, so u is constant, it's not changing with time, right? What it means is that whatever shape it takes initially is just going to translate, right, with a distance of ct. Okay, so this is what I illustrate here. What it means is that if I start off, this is u and x, if I start off with some initial bump when t is 0, okay, as time goes on, this thing does not change form, it just translates along the t, or if you like, along the characteristics. Okay, so it's just going to translate. At each time, it's going to move a distance of ct. Okay, so that is shown by here. Here, I made this using GeoGebra. Okay, and you can do that using this function here. That's what I used. Okay. Anyway, it's just a schematic to illustrate this. So the solution is fixed. So the method of characteristics is actually very powerful. There are whole books written on it if you are looking at the theory of PDEs. Okay, so you can look at it later on. Here we are just using this to help us with the numerical methods that we're going to introduce. So it can be extended to variable coefficients when c is variable, function of x and t. Okay, now for linear problems, the characteristics do not cross each other. Okay, so you just have, you know, if you like, lines or curves that do not cross. When you are dealing with non-linear problems, those characteristics can actually cross, and you get what is called a shock. Okay, but it's a powerful method which can actually be used to tackle some non-linear problems. Okay, so what it means is that having a background to the theory, the method of characteristics, tells you that when you are dealing with the numerics, you have to be mindful of the characteristics of the equation, of hyperbolic equation, when you design a numerical approach. That is why we basically looked at this. Okay, so later on in the next lecture, we're going to look at the finite difference approach instead of, you know, this theoretical approach to the equation. All right, so I'll end this lecture here, and then we'll look at the finite difference methods next. Okay.